All right, today we are doing section 1.2 on inductive reasoning. We are going to use inductive reasoning to make conjectures, and we will talk about what those are in just a minute. First, for our warm-ups, 1 and 2, we need to evaluate the expressions for the given variables. An easy way to organize your answers for this would be to make a table. So like x versus x squared. If you didn't do it this way, that's not a big deal. This is just how I'm going to organize it. So I know for x, I'm plugging in 1, -1, and -2. And I'm evaluating x squared for those values. So my answers will go below. If I take 1 and square it, what do I get? 1. 1 times 1 is 1. What about -1 squared? +1. Remember, a negative times a negative comes out positive. So -1 times -1 is a +1. What about -2 squared? A +4. Very good. All right, the other one, hopefully you have more room than I do, but I'll try to squeeze it in down here. So we're going to have x versus x plus 2 times x minus 2. So my table's going to look a little funny. And we're plugging in 0, 1, and 2. Questions so far about how I'm setting this up, why I'm setting it up this way? This should be a review from algebra, even if you wrote it out differently there. Oh, I didn't close my other parentheses. Okay, so this is going to take a little more mental math than the last one. We plug in 0 for both x's. So 0 plus 2 is 2. 0 minus 2 is -2, and I have to multiply those two numbers together. So 2 times -2 is -4. All right, we're going to plug in 1 for both of our x's. 1 plus 2 is 3. 1 minus 2, -1. 3 times -1 is -3. Finally, we plug in 2 to both of the x's. 2 plus 2 is 4. 2 minus 2, 4 times 0 is 0. Questions about that review from algebra? Okay, then the next part is a review of what we did last week, looking for patterns. Describe a pattern, write the next number you see. Obviously, I don't have a lot of space here, but we'll do our best. Did we notice a pattern on number 3? I think I've heard some people say it. -7 or subtract 7. Subtract 7 is our pattern. What would the next number be? 72. All right, did we see a pattern on number 4? What did we do? I think I heard somebody say something with an 8. What did we do with 8? Add 8. Our numbers are getting less negative. They're moving towards a positive direction. So we are adding 8. That one's a little tricky. If you were to say subtract a -8, technically you'd be right, but it's just easier to say add 8. What would our next term be? -11. Questions before we do number 5? All right, on number 5, Alicia's savings account balance was 55 at the end of March, 63 at the end of April, 71 at the end of May, 79 at the end of June. Predict the amount she will have in her account at the end of July. What did we come up with? What pattern do we notice between these amounts every month? They're going up by 8. So we're going 1 month into the future. We're going to guess that her account will again go up by 8, and her balance would be $87. Okay, so let's talk about these real quick. They're pretty straightforward. A conjecture is an unproven statement based on pattern or observation. So we don't necessarily know if it's true or false. It's just a statement we're making based on things we observe. Kind of like on that last warm-up where we said she would have $87 at the end of July. We don't know that. Maybe she'll save $10 instead of $8. Okay, but we were noticing a pattern, so we were making a guess. That's a conjecture. Inductive reasoning is that process of looking at patterns and making observations. The counterexample is an example we use to show that a conjecture is false. Okay, so we come up with an example to prove ourselves or prove a statement wrong, or why that cannot always be the case. All right, a lot of what we do today and throughout the rest of the year in geometry is going to be about looking for patterns. So we come up with examples sometimes. We are going to make situations that develop a pattern, hopefully. We make a conjecture. So we use those examples, some of which we may have come up with on our own, to try to see if anything is in common or something that's happening the same every time. And then we verify it. So we try to show that it's true in all cases. Or we come up with a counterexample to show that it's false, meaning we're going to go back to square one, look for a new pattern. All right, on number 1, we are trying to complete the conjecture. The sum of any two odd numbers is. You might already know this, okay, but if you don't, we're going to look at examples to try to find the pattern. So we want to choose two odd numbers at a time. Sum means we want to do what with them? Add them together. Let's see if we notice a pattern. So it doesn't matter to me. Give me two odd numbers. 1 and 3. So I'm going to add 1 and 3 together. Use a different ink color. Is that any better? Well, if we add 1 and 3 together, what do we get? 4. I'll just test out different colors. 2 more odd numbers. 5 and 7 would give me 12. Anybody else have any other odd numbers they want to try? 13 and 1? Is that what I heard? Yeah. Okay. 13 plus 1 would give me 14. So what do I notice about all these answers? They're even. So my conjecture would be that the sum of any two odd numbers is going to be even. Okay, so on number 2, we're looking at the sum of the first n positive odd integers. So that's a little weird. So if I was just looking at n equals 1, I'm just looking at the first positive odd integer. There's nothing else to add to it, so its sum is just 1. So that one's kind of weird. We don't really need to look at that one a whole lot. But if n equals 2, nope, let's go with 3, because we're doing, well, let's just go with 3. Keep it odd the whole time. So we're looking at the first 3 positive odd integers. So the first one is 1 plus, what's the second positive odd integer? 3 plus, we're looking for another one. We wanted 3 positive odd integers. What's the next one after that? We had 1, 3, 5. We're going to add those all together. What do we get? 9. We could have done 2. We're trying to make it a little more interesting. Okay, if we're not sure about this pattern yet, let's kick it up and go to 4. So I know I still am going to be using 1, 3, 5, and then what would I add to that? What's the next positive odd integer? After 5? 7. And when we add all those up, what do we get? It's basically this number plus 7 is 16. Is anybody noticing something about these numbers? All right, so we're noticing that these sums are the squares of our first column. 1 squared is 1, 3 squared is 9, 4 squared is 16. So if we're just using n in general, we would say that it's n squared. We're taking that number of terms and we're squaring it. Some of these relationships are going to be easier to come up with than others. The product of an integer and its opposite. So give me an integer. I think I heard 5. What's its opposite? -5. And product means we want to do what? Multiply them. What's 5 times -5? -25. Okay, somebody give me another integer. 3. What's its opposite? When I multiply them. Let's do one more. Give me another integer. 6. What's its opposite? And when we multiply them. Okay. So again, this one's probably a little easier to come up with, but it might be harder to write it in the right terms. So I'll help you out with that part. What do we notice again about these numbers? Much like the last one, we've got, they're perfect squares, but they're all negative. Okay, so we're going to have the opposite of the perfect square of that number. So -n squared. All right, so on to A. We are multiplying odd numbers together to see what the product comes out to be. So we've got 3 examples we came up with here. Do we see any relationship between the answers to those? Every time they're odd. So the product of any 2 odd numbers is odd. For the sake of time, I'm going to go through B a little bit quicker. So this would be a similar table to what we saw in the beginning, right? N and n minus 1 times n plus 1. It's a similar table. What do we want to use for n? Give me 3 different numbers for n.
2, 4, 6.
2, 4, 6. I like it. Okay, so when I plug in 2, 2 minus 1 is 1. 2 plus 1. We multiply 1 times 3. We get 3. Plug in 4 for both ends. 4 minus 1 is 3. 4 plus 1 is 5. So we've got 3 times 5. We get 15. We plug in 6. Six minus 1, 6 plus 1. We multiply them, 35. Okay. This pattern is a little harder to see. I don't think I'd ever give you one this challenging on your own unless it were like a bonus or something. But what we are doing here is we are squaring n and then taking 1 away, right? So 2 squared is 4. We take 1 away, we get 3. 4 squared is 16. Take 1 away, we get 15. Right? That's what's happening here. So really the answer here is n squared and then take away 1. Again, I don't think I would ever give you one that challenging unless it were a challenge bonus type problem. Are we ready to go on? All right, let's do it. Show the conjecture is false by finding a counterexample. So our conjecture is the sum of two numbers is always greater than the larger of those two numbers. And we're going to try to come up with an example that shows that this statement is not always the case. So I'm telling you right now, this is not always the case. We need to come up with an example to show that. So let's just give me two numbers for starters. This might not be our answer yet. 6 and 2. Okay, so this is saying that I'm taking the sum of two numbers. So in this case, I'll take 6 plus 2. What would I get? 8. This conjecture says that the sum, 8, should be bigger than the larger of my two numbers. Is it? Yes. So this shows that it's true. So this would be like, oh, okay, so this might work all the time. Can we come up with one that maybe doesn't? So let's use a negative. Which number should we make negative? 6? So if we take negative 6 plus 2, what do we get? Negative 4. So which of these two numbers is bigger, negative 6 or 2? The 2 is bigger, right, because it's positive. So is negative 4 greater than 2? No. So this one does not work. So that would be our counterexample. We want the one that shows that it does not necessarily work. This one showed that it did work, and that's great, but that doesn't help us out. Does that make sense? We're looking for the one that shows that it doesn't work. All right, if the product of two numbers is even, then the numbers must be even. So we're trying to find an example that shows that's not always the case. So we're multiplying two even numbers together and get an even number. Well, that's always going to work, right? So what's a situation where we multiply two numbers together, we end up with an even number, but we didn't start out with even numbers? This one's a little weird because we've got to come up with what we're starting out with a little differently. So let me give you an example. If I can come up with one off the top of my head. So I think I heard somebody say 2 and 7. If we take 2 times 7, we come out to get 14. So we came out with an even number, but we didn't use both of those numbers to be even. So this would be a good counterexample. One number was even, one was odd, but they multiplied to an even number anyway. All right, this one says, if the sum of two numbers is positive, then the numbers must be positive. Do we have a counterexample? Or just two numbers? We can just try some until we come up with a counterexample. Nobody wants to give me numbers. 6 and negative 2. All right. So if we take 6 plus negative 2, what do we come up with? A positive 4. Okay, so this said that if the sum is positive, which our sum is positive, then the numbers must be positive. But they weren't both positive, right? We had one that was negative. So this would be a good counterexample to show that this statement is not always true.